All right, Patriots, welcome back. My name is Mr. Love, aka the Math Patriot, giving you another lesson in the fun and exciting world of high school geometry. Now, let's go ahead and move on with our lessons. Just so you know, I am not doing a live session in class right now. I'm actually recording this from my home, and there's not a live class in front of me, which means you will not be having all of those wait times where I'm letting my class copy. You'll also notice that I'm not going to be actually writing a lot of stuff. This is all done on the PowerPoint just to make things flow a little faster. So if you need to pause this or take some time to write stuff, just hit that pause button and we'll just keep on going from there. Now, last class period, we went over a bunch of stuff having to do with algebraic proofs. We went through and we practiced how to basically solve an algebra equation using the double column proof method. And the reason we did that was, quite frankly, just to basically give you an idea of how that proving system works. And so let's go through and let's actually practice another one of those. So first off, we've got 1/5 x plus 3 equals 2x minus 24. We want to prove that x equals 15. Always nice that we actually give you the answer on these proofs. So start off, as always, we're just going to go ahead and take that original statement and write it down. And then over here in our reason column, we're going to call that the given statement. Now, you'll notice that I spaced all this stuff out over here, all this blank space, and that was just so that we can have everything lining up on our next steps. So as I'm looking at this, what I want to do to solve is I need to get all of my variables on one side, numbers on the other, and I'm going to accomplish that by first, well, copying everything down and then seeing what I'm going to do. I believe I need to clean up this 3 over here. So I'm going to subtract 3. Notice what I do on one side, I do on the other side. So minus 3 on the left, minus 3 on the right. We're also going to clean up this 2x. So I'm going to subtract 2x on the right as well as on the left. Now, because I'm subtracting both of those and I'm doing it on both sides, the reason I'm going to invoke is the subtraction property of equality. Now I'm going to go ahead and clean that up. My negative 3's are going to subtract out. My 2x's are going to subtract out. Then over here on the left, I've got my 1/5 x minus 2x is going to give me negative 9/5 x. My negative 24 minus 3 gives me negative 27. Now on to my next step. Oh, by the way, sorry, that's a substitution because I'm substituting negative 3 or plus and minus 3 for 0, and then 1/5 for negative 2x gives me negative 9/5, etc. All 4 sets of those. Okay, next up, I need to clean up this negative 9/5 over here. The way I'm going to do that, I could divide by 9/5, which is effectively the same thing as multiplying by the reciprocal. I'm sorry, I'm going to write that down again. We're going to do that by multiplying by 5/9. And I wrote that as the division property of equality. Technically, it's also the multiplication. Dividing by a fraction or multiplying by the reciprocal is basically the same concept, but we multiplied by the reciprocal. The reason for that is the 5's are going to cancel, the 9's are going to cancel, and also the negatives are going to cancel, leaving me with just x on the left. So I'm substituting here. I'm also substituting here. Negative 27 times 5/9. If you don't know how to do that one in your head, well, first off, negative times a negative is a positive. And I like to reduce first if possible. 27 divided by 9 is going to give me 3 times 5 is 15. So my result there is x equals 15. And once again, that is a substitution step. So you'll notice that on these algebraic proofs, we're essentially just overcomplicating the issue of solving an equation. The reason all of this is important is because when we get to geometric proofs here in the next few minutes, we want to get used to the idea of systematically showing every single step that we've done all the way down, no matter how tedious it is. The one that students typically think is the most tedious is having to write this substitution here. And you're going to see that actually quite a bit in our geometric proofs. So with no further ado, let's go ahead and jump in there. Now, the most simple object in all of geometry, with the exception of points, lines, and planes, are undefined terms, is a line segment. Now, we're only going to deal with 2 postulates in our with our line segments today. The first one is the Ruler Postulate. Now, I don't believe I've ever actually called or use the ruler postulate inside of a proof, the place that I use it is really just as a facilitation for the segment addition postulate. What the ruler postulate says, and you can read it verbatim if you want to, but essentially every single line segment, if lined up against a ruler, every point on that segment is going to correspond exactly to a location on the ruler. Now, it corresponds to a real number as opposed to an integer, which means it could be a decimal. So this point right here could correspond to 1.5. This point, let's go back. This point right here could correspond to 2 and an eighth, which is 2.125. Now, sorry, my thing keeps on trying to advance on me. The reason that's important is because the fact that I can measure the distance between any 2 points is important for the idea that I could then come in and add those segments together. You see, this distance here from A to B has a distance. The distance from B to C has a distance. And since they're essentially just adding up 2 sections on a ruler, such as adding this and that between A and this, let's just call it C here, from A to C and from C to B, well, by adding up this distance from A to C plus from C to B, the left plus the right gives me the whole thing. So the segment addition postulate is going to be invoked anytime that I have 3 collinear points, important that they're collinear, and that the middle point is between them, which again means it's going to be on the same line. Then AB, the distance between these two, plus the distance between these two, AB plus BC equals AC, which is what I have here. Now, that's going to be important for us as we're moving forward, and we'll use that postulate several times today. Remember, anytime we have 3 collinear points and we're going to need to add up the 2 segments to make the larger one, we're most likely going to be invoking the segment addition postulate. So, also, another thing to keep in mind for our geometric proofs is that there's a difference, first off, between these concepts here and those concepts there. The main difference is the fact that this section, or this slide, has all of these symbols on it, the set line segment symbols, whereas these do not. The difference in the two, notice that this without it is talking about the distance from A to B. So this is essentially a variable for the distance from A to B. If I was looking at this particular side, AB equals 3, sorry, let me get my, AB is equal to 3 inches because it's from A to B is 3. AB with a line segment over it is the actual physical object right there, okay? So important to keep those two separated. So our distances, or our lengths from A to B, is reflexives, which means something is equal to itself. It's also symmetric, that I have the authority or the ability to take whatever on the left and move it to the right. So here AB is on the left, here it's on the right. I can just flip those two out, okay? Which we know, we've written this type of stuff before. X equals 3 and 3 equals X are essentially the exact same thing. Equality is symmetric. Also transitive. If AB equals CD and CD equals EF, then AB equals EF. So basically notice that since CD is in both those equality statements, I can then use that to bypass and jump over to EF directly from AB. Now, this is essentially a substitution idea, and think about this in terms of essentially like a big old box train full of cars. You've got a whole bunch of cars in the middle, and all of these guys are equal to each other. Sorry, my pen's acting weird and not wanting to give me good markings here. But if every single one of these is equal, and this guy is 5 right here, because every single one of these is equal, I can then trace that 5. The 5 is going to go there, then there, and all the way here. Now, in a proof, I don't want to have to write every single one of these equality statements, so the transitive property lets me jump all the way from this engine all the way to the caboose, that since this is 5, that is 5. So if I have this long series of equality statements, then I can jump straight from the beginning to the end, provided that I have this breadcrumb where CD is the link, and then so like this would be AB, this would be CD, this would be EF, all the way through to whatever XY, and the beginning equals the end by the transitive property. Okay, so we know that's true for numbers, but that also works for segments as well, all three of those properties. Segments are reflexive. Notice here that instead of an equal mark, I have a congruent symbol because segments, objects are congruent, same size, same shape, whereas measurements are equal, as in they have the same numerical value. But the transitive property, reflexive property, and symmetric property apply to all three of those as well. Okay, enough of that. Let's jump into our proofs. Now, first off, if AB is congruent to CD and CD is congruent to RS and AB equals 12, then prove that RS equals 12. Well, a picture is always worth 1,000 words on these. I'm going to go ahead and draw in A, B, and C, D. Now, I know that AB is congruent to CD, and I know that also CD is congruent to RS. Now it makes logical sense that since AB is congruent to CD and CD is congruent to RS, now there's a reason that I put this double mark here as opposed to a single, because I can't just go ahead and jump in a single mark, a single hash mark, because that's not what the given statements say. It says that these two are equal and then those two are equal. So I'm using those different marks to show what was in there. Also, I know that AB equals 12. What in the world is my pen doing today? Okay. So I've got to somehow show that RS is 12. Now, we can logically see this, that since those two are equal and those two are equal, then the 12 could essentially get copied down here to the RS, which is, as a rather simplified version of that transitive property we talked about a second ago. So we might use transitive, we might use substitution. Let's just see how we did. Like I said, I typed this up, so we'll use whatever's on the slide. So always for our proofs, for our double column proofs, we want to take our original information and copy it in as the given. So there we go. Copied in AB is congruent to CD, CD is congruent to RS, AB is equal to 12, and I apologize, that should not be there because that's what I'm trying to prove. That's in the then portion or the conclusion and not the hypothesis. So let's pretend that's not there. Now, the reason for that is it was just given to us. Now, let's go ahead and look at our next line. Since I know that AB is equal to CD and CD is equal to RS, I'm going to use those two to say that AB is equal to RS. Now, we do that by using either substitution. You also could have used the transitive property. Okay. Now from there, since AB is congruent to RS, I need to somehow get to the fact that these segments are congruent. Now, I don't know, I'm sure the segment lengths are equal because this over here has to do with length. Now, I've got to figure out a way of converting from segment length to, from segment congruency to segment length. The way that I do that is by, first off, copying down the congruency statement, but this time without the bars and without the symbols and without the squiggle to make it congruent. Now, the reason I'm allowed to do that is because of the definition of congruent segments. Congruent segments have equal measures, so I'm allowed to make that conversion. Now that I know that the length of AB is congruent to or equal to the length of RS, well, and the length of AB equals 12, length of AB equals 12, then I know I can substitute in, replace the AB with a 12, which is what this is doing right here. I'm able to do that by a substitution step. And then here I've got 12 equals RS, but up here in the top corner, I'm looking for RS equals 12. Now, I'm allowed to flip that around, and if you remember back on the previous slide, the thing that allows me to flip it around from 12 equals RS to RS equals 12 is my symmetric property of equality. Now, I finished with this. I'm going to add in a small little tidbit at the end of this that I want to make sure that we're doing on every single proof. And we want to have some way of symbolizing that we're done, that we've proven what needs to be proven. So there are several ways of doing this. The first one is a symbol like this, a box with a there that is shaded in. You'll actually see several literary magazines. I believe Time Magazine and National Geographic are the one I've actually seen do this. There are probably many others that do. But if there's a multi-page article and you finally get to the end of the article, you'll notice at the bottom of that page in the bottom corner, there's a little shaded box down there. It's just a way of showing we're finished with what we were trying to do. So when you get to the end, whenever I've got that this exactly shows what it asked me to, I can put a little box there. Another symbol that gets used is two vertical lines with little hitches on the bottom. Sometimes it'll get combined into this thing as like an upside down pie. That's a very medieval symbol. It's the idea of two swords being drawn in parallel. And whenever two knights are holding their swords parallel, vertically up and down, they're not attacking one another, as opposed to two swords that are held like this that are clashing each other. This is the symbol for contradiction. Man, my pen is really acting up today. That's a contradiction, whereas this is in harmony, or things are lined up together. This means that I have proven what I meant to be proven. So we're not using the cross swords, we're using the parallel swords. Now, another one that gets used is just let me go ahead and erase this out because that doesn't work, is just the three capital letters Q, E, D. And QED is actually the one that I prefer. And you'll see down here at the bottom, here's what that actually stands for. It's a Latin abbreviation for quod erat demonstrandum, which means essentially, and this is a bad translation, that which was to be proven, or thus it has been demonstrated. So I was trying to demonstrate that RS equals 12. I have shown RS equals 12, therefore QED. Now, QED is my favorite way of showing that a proof is finished, and so you'll see me using QED quite a bit. I think it just sounds sophisticated. Okay, moving on to example 3. If CE is congruent to FE, so I know that CE is congruent to FE. Also that ED is congruent to EG, ED and EG. Then show that CD is equal to FG. Now CD is this full length and FG is the full length. So we're trying to get to here. Now, just like always, we're going to copy in our originals as our given reasons. Now, just brief little roadmap here. I always find it good to look at a roadmap of seeing where I want to go. I'm going to need to, or I see that I have F, E, and G are 3 points that are collinear, and I have C, E, and D that are 3 points that are collinear. It makes sense to me that I'm going to have to use my angle addition postulate to show that these two added together equals FG and that CE and ED added together equals CD. So I'm probably going to have to use my angle addition postulate, and then I'm going to have to do some substituting to show that CE and FE are congruent, and somehow make that whole thing in the end show that CD is congruent to FG. All right, so let's see where we go from there. Now, because the angle addition postulate does not work on line segments, it works on lengths, it's necessary for me to convert these guys to the lengths of them. So I'm just invoking the definition of congruent segments, just like we've done before. I'm going to copy it down, take away the line segment symbols, and take away the top little squiggle of the congruency mark. Okay, next up, since I have my segments that are adding up, my 3 sets of 3 collinear points, I'm going to go ahead and invoke the the segment addition postulate. So CE plus ED equals CD, that's the top one. The bottom one here is that FE plus EG is equal to FE plus EG is equal to FG. Now, the reason I did that there is I want to show you what I'm doing on the next line is I'm just going to first off take my original statement here and bring it down. Now, if you're doing this in pen, you might want to wait up a second because there's going to be some erasing that essentially happens here. I'm going to do some substitution because I want to do in the end is show that CD equals FG. I've got to somehow convert this statement to something that's going to allow me to get CD over on this left-hand side. Now, what I'm going to do is I'm going to look for FE somewhere in here. I see that FE is congruent to CE. So what I'm going to do is take this CE and bring it down and replace it in there for FE, which is what I'm going to go ahead and do now. Bring that guy down. I also now see that I have an EG right here. EG, and I've also got an EG right there. EG is congruent to ED, so by the same route, I'm going to go ahead and take that one and bring it down. Let's just go ahead and do that. Bring ED down, and there we go. So I made a substitution there, so I'm going to call that my substitution as my reason. Okay, now moving on from there. I also see that I have CD plus ED here and CE plus ED there, which means on my next line, I'm going to go ahead and again copy this thing directly down, but then replace this CE with plus ED with my CD and bring that down as well. I believe I went the other direction, but boom, there we go. So I know that the distance from C to D is equal to the distance from F to G. However, I'm looking for segments that are congruent, and I'm allowed to convert back from distances to segments using my, sorry, I forgot my substitution step there. Anyway, I'm allowed to convert back to the line segments themselves by the definition of congruent segments. So now I have proven what I set out to prove. Therefore, I've got my big fat QED, and I promise it says QED. My pen is just being crazy today. All right, moving on to example 4. Please remember, if you need to, pause this at any time to get this stuff copied down. All right, example 4. Again, let's go ahead and copy in all of our original information. Here, the only thing I have is that AB is congruent to CD. So AB is congruent to CD. Now, I'm wanting to show that AC, which is this distance here, is congruent to segment BD, which is that distance there. I really need to get my pen checked out. That distance there. Pretend that didn't happen and I can't do anything about it. All right. So again, as I'm looking at this, I'm seeing that I'm probably going to have to use, I've got 3 sets of collinear points on this distance here. I've got, again, another set of collinear points that are this distance here. Again, I'm probably going to have to use the segment addition postulate, which means if I have the segment addition postulate, I'm also going to have to convert this guy, or also this guy here, to the lengths as opposed to the segments. So basic roadmap, I'm going to have to convert this to segments, to lengths, and then do my segment addition postulate, then do some substitutions. All right, so AB is congruent to CD. There's my given information. Let's go ahead and convert that over. Definition of congruent segments, just like I've done before. Now, next up, I'm going to invoke my segment addition postulates. So AB plus BC equals AC. That's what I've marked in top on red. BC plus CD equals BD. That's what I've marked in bottom in red. And that is my segment addition postulate. Now I need to do some substitution. I'm not going to do all the fancy, moving around with the animations on the PowerPoint. I'm just going to go ahead and start showing what I have here. Here I've got BC got written down directly, BD got written down directly, and I've replaced CD with AB. I'm able to do that because of this. CD equals AB, so this CD is replaced with AB. And that is a substitution step. So that's where that came from. Next up, I see BC plus AB here, and I've got BC plus AB here. Yes, it's written backwards, but addition is commutative, so that's the same thing. So I'm going to replace this here with an AC. So, I'm sorry, I used the wrong thing. This is going to get replaced with AC because of that AC there. So the distance from A to C is equal to the distance from B to D. Again, that's another substitution step. Now I'm almost there. Again, I need to know that the segments are congruent. Well, equal lengths means congruent segments. And forgive me, I was supposed to put a D there. And let's see if my pen will agree with me. And that is segment BD. That's the definition of congruent segments. And once again, I've got a QED. I promise that's an E. My pen does not want to work with me today. Okay, moving on. Last one, and probably the most complicated picture we have on the entire thing. Now you're going to notice that I'm going to do some of that I guess, geometry ninja stuff with my segments markings here. I'm going to go ahead and get given statements in there. Notice that these are all written as lengths as opposed to segments, so I don't have as much to do as far as the definition of congruent segments. So first off, AC is congruent to AB, and then AB is congruent to BX. I'm going to go ahead and put my doubles there. And I'm going to come back to this CD equals XY in a second. Now, again, I've got to use my substitution or my transitive property to get all the way from AC and AB to BX. What I'm trying to show here is that AY, which is this distance, is congruent to BD, which is that distance. And so I've got to, again, I'm probably going to use my segment addition postulate on this, but before I can do my segment addition postulate, I need to know that AC and BX are equal to each other. All right, so let's go ahead and say AC equals BX. I'm able to do that because of, again, this AC equals AB and AB equals BX. I'm going to substitute that and get AC equals BX. That's a substitution step. Now, once I've done that, I can then go ahead and mark this as a single mark, or a single hash mark, because I know AC and BX are equal. All right, now, because I'm going to need to invoke or get all the way from A to Y, I'm going to go ahead and invoke my segment addition postulate. AC plus CY equals AY, BX plus XD equals BD. It's my segment addition postulate. Now, I told you I'd come back to that. CY is equal to XD. So I'm again going to do something similar to what I did I guess, for the previous two. And I'm going to take, well, let me back up a little bit. I'm going to take this BD and just bring it down. This XD, when I bring it down, I'm going to replace XD with CY. So you're going to see a CY right there. The BD is going to get copied down. Now you'll also notice when I bring it down, my BX, I'm going to replace BX with AC. Now, I could have replaced BX with AB, but that doesn't help me because I'm looking for this guy. So I'm choosing the one here that's going to help me get there. All right, so that's where those are coming from on that substitution step. You're going to see I've got BX plus CY equals BD. That's a simple substitution step. And now, since I have AC plus CY here and here, I'm going to bring that AY and put it right there. So I've got AY is equal to BD, which is exactly what I was looking for. That's my substitution step. And, well, I'm done. So I've got my QED right there. All right. Well, that's all we've got for now. That's all we're doing with our congruent segments and our geometric proofs with segments. Next time we'll come in and we'll do this with angles. And I'm just warning you right now, you might want to go ahead and practice these on any assignments that you've got from me or your teacher if you're tuning in from YouTube land, because angles have a lot more involved stuff than segments, and so we've got more postulates we've got to deal with. So go ahead and get practice on these, and I will see you next time. As always, please stay patriotic.